So for this one, we got to simplify this exponent type stuff, which we just finished the unit on this exponent rule stuff. So if I was to simplify this, I would see that I'm dealing with parentheses right here. So that means the base will stay the same as an R. And since we got the parentheses, that tells us that we will be multiplying the two exponents of 6 and also 3. So we have base R still, but now I got 6 times 3, which is 18, and that's all we need to do for this one. Two objectives for today: I can memorize the first 12 perfect squares, which we'll talk about, and also I can simplify any radical. So we'll take 30 seconds and copy that down, please. So we're going to look at perfect squares, which have to do with exponents. They're gonna help us understand how to deal with radicals, because they are inverse type operations, just the same as multiplication and division are inverse operations, and also addition and subtraction. So starting off here, we got powers or exponents, because they're the same thing. Exponents of 2. So if you see an exponent that is 2, it indicates that a base is being multiplied by itself twice. Okay, so something like these two examples, right? You got 5 to the power of 2 with an exponent of 2 right there. That would indicate we got 5 times 5. Okay, something times itself. Or you could say, you could use this with even letters, right? X to the power of 2 is the same as x times x. Okay. Now, as it turns out, this is the same strategy we use when we try to find the area of a square. So if you had some kind of square here, something like this, and you knew the side lengths were 2, you'd have 2 and 2. But if you wanted the area, which is how this is related, you'd say you got to take 2 times 2, which is the same as 2 to the power of 2 there, okay? So this is why when we see something to the power of 2, you may have heard this said as something squared. Okay, so like this reads 5 to the power of 2, but if you wanted to, you could read it as 5 squared. Or this one, x to the power of 2, you could also say x squared, okay? It's because when you multiply something by itself, that's how you find the area of a square with those specific side lengths. Okay, so yeah, there we go right here at the bottom. 5 to the power of 2 is fine, but you can also just say, if you wanted, 5 squared. So when you see exponents of 2, we just say that the base is squared. So that brings us to square roots. So when we're talking about square roots, the root is really the value that's being multiplied by itself. Okay, so what value multiplies by itself, or the value that's being squared? Okay, and that's kind of what we mean when we say the root value, base value that is squared. Okay. Now we see this new symbol right here. Okay, that is a square root symbol. So when you see something like that, we read it as a square root. Okay, but we're not going to write square root in words like I just did right there. You're just going to see that symbol, and you need to know that it means square root, or that it reads as square root using that specific symbol. But again, right here you see the square root asks what the side length of a square is given the area. Okay, so if you have a square root, so this is our square root symbol, and mine don't usually look that good, but whatever. What's on the inside of that is the area of some square. Okay, but what it asks for you to do is to find the side length. Okay, so whatever you get out of this will eventually become, or would be, the side length from whatever that area is. Okay, so when we see something like this is the square root of 100. That's how that reads. That's how that reads right there. But it's the same thing as saying, if you have the area of a square that's 100, what's its side length? Okay, so, or what is the side length of a square if the area of the square is 100? However you want to think about that being worded. Okay, so in this case, let's see. Let's say we had a square. That was technology, so that's not too bad. But we're saying we know the area here would be 100. So then we need to find the side lengths. Now again, the unique thing about the squares is that the side lengths are the same. So you just got to figure out what those side lengths are. So again, what number multiplied by itself is 100? That'd be 10. Okay, so the side length here each side length is 10, whatever units that is. All right, which means that if we saw this just out here and they said, evaluate this, we'd say, okay, well, we know the square root of 100 is 10. The side length of that square would be 10. Now, I may be making that more obvious than it may be for you guys right now, but with some experience, hopefully that will help. Okay, so you may have to sit down and think, look at these, and again, you're asking yourself, what number multiplied by itself is whatever this number is, okay? So this number on the inside of the square root symbol is called a radicand, and the square root symbol is a type of radical. I don't know. We're never going to actually test you guys on that language, but we may use that vocabulary from time to time. All right, what we're looking at here is perfect squares, okay? So, what the crap is a perfect square? Well, a perfect square is, it's when you take a whole number and square it. Okay, well, then what's a whole number? A whole number is not a fraction or decimal. Okay, I mean, you could write these as fractions or decimals, but they don't generally just show them, okay? Now, we're talking about the base. The base, right? The whole number is the base, and then you square it. So like right here, this is the base, 1 squared, 2 squared, 3 squared, 4 squared, and then you get these numbers right here, which are the actual perfect squares, okay? So perfect squares is this list of values. Okay, now here's the nice thing about these is when you see them here, right, in all these square roots, right, you take the square root of any perfect square, and what do you get out? You get out the whole value. These values right here, right? 1, 2, 3, 4, 5, 6, 7, and this of course goes on forever. But you really just get the base of whatever the number was that was squared, okay, that base number. But there's the expectation that you'll have these memorized, because I believe on the first couple lessons for this unit, they're saying no calculators, all right? But when you see a perfect square being square rooted, you know that you just get some kind of whole value out. Okay, now here's the other thing too, is if you take the square root of a non-perfect square, unless there's small conditions that, although I don't think we really care right now, then you get what we call irrational numbers. Well, I guess you probably don't care about that either. But again, I'll just reiterate this. The sooner you guys have these memorized, the faster this kind of stuff will go. Because we're going to see stuff like this, okay? Square root of 16. So this is how this reads. I guess it'd be a question, what is the square root of 16? So we're trying to evaluate this. Okay, so that's kind of the surface of the question. So what is it actually asking? It's asking what number multiplied by itself is 16. Okay, well, what we just saw here on that last slide is that 16 is a perfect square. So we're expecting some kind of whole value to come out of this, right? 16 is a perfect square. So when we say, hey, what's the square root of 16? We're expecting no decimals, no fractions. And so, again, you may have to sit here and think about this while we're not using calculators. What times itself is 16? It's 4. 4 is, right? How about something like this? So again, this is how this would read. This is the negative square root of 256. All right, that's pretty nice. But again, it's asking, forget about the negative for now. It's saying what number multiplied by itself is 256, then just make it negative in the end. Okay? And that's what that negative is telling us to do right there. That's an order of operations thing right here, because technically the square root could be considered parentheses or even exponents. And then the negative would be a multiply. So that's an order of operations thing, okay? So what number multiplied by itself is 256? Well, if we have the chart memorized, we know that 12 times 12, well, that'd be 144, okay? So there's going to be a little work here, and this is where I think a calculator would be fine, right? So it's saying, well, what about 13 times 13? If I can type that in, right? And I get 169, okay? So 13 times 13 is 169. Now, we need the same number multiplied by itself to be 256. So I'm going to keep going, and it should be fairly close, okay? So 14 times 14. See, I'm using a little bit of guess and test right here, but I'm using it in a more systematic way. 15 times 15, I believe it's 225. But you see we're getting closer to 256. So 16 times 16, I get 256. There we go. Okay, so now I know that the square root of 256, it needs to be 16. But now this is when, like it says there, I've got to make it negative in the end. There we go, negative 16. All right, how about this one? We're going to evaluate it to, okay, nice. Well, again, what number multiplied by itself is negative 36. Now this one's different because the negative is on the inside. So we actually need to think, what number multiplied by itself is negative 36? And that's what this one would read, square root of negative 36. Now, I think with some thought, you'd say, well, maybe 6 times 6. Well, the problem with that is you get positive 36 on that, not negative 36. Fair enough. Well, let's just say negative 6 then. Negative 6 times negative 6. Remember, it has to be the same number multiplied by itself, even if it's negative. The problem with this is it also gives us a positive 36 value, which tells us right here, this one's just not real. What the crap does that mean, not real? Well, that means that you could find a value that would make this work. It's just not real. So you're telling me there's such a thing as a not real number? That's correct. We just don't care about that in 8th grade math, all right? And, I mean, you know, what is that, like 10th or 11th grade kind of math? But it just, for now, all we got to say, hey, this one's just not real. Okay, so this now is a decimal. So is this perfect square? Maybe. Well, here's the thing with this one is, I see 49, and 49 is one of the perfect squares, right? I know that 49 is 7 times 7. Okay, that's a pretty good start. Okay, well, the decimal, what do we got here? This would be the same as, let's see if I can spell this right, 49. That'd be 10,000. 10,000 that year. Which, yeah, it is very small, right? But that means I can actually write it as a fraction of, again, it's 49 over 10,000. And we can actually take the square root of this fraction. So this is kind of a special case scenario. So what does this mean for us? Well, it means that instead of taking this as a whole fraction, what you can do, one of the rules you can do with square roots like this, is you can take the same fraction, 49 over 10,000, and you can simply just square root the numerator and denominator separately, okay? And that's why I was pointing out the square root of 49, we know, is 7. Right, 7 times 7 is 49. And the square root of 10,000, this one may take some thought, but it's going to be 100, okay? How do I know that? Because it's got 4 zeros, I just divided that by 2, so I know the answer has 2 zeros with a 1 in front. That's a nice little nifty trick if you see some kind of base 10 value, but I don't know, whatever. So our final answer here, I'm just going to keep this as, well, you know what? That's the fractional value. You could write it as a decimal as well, 7/100, like this. It's the same thing. So this gives us this rule right here. If you ever have a square root of a fraction, it's okay to split it up. So that you're just taking the square root of the numerator and the denominator separately. And the nice thing for now is that they're not usually going to give us values in the fractions that are not perfect squares. Well, they may give us a negative in front, but again, we know that the negative in front is just applied to the answer, whatever it is. Okay, so I'm going to take this, it's negative still, the whole fraction will just be negative. But I'm going to take the square root of the numerator and denominator separately. And the nice thing is, I know that 1 is a perfect square, and I also know that 64 is a perfect square. Now, this comes with a little bit of confusion from time to time, because students look at 1 like, well, what the crap would you multiply by itself to get 1? It's 1. That's the great thing about 1. Multiply it by itself as many times as you want. In infinite times, you get 1. But what number, again, we're looking at the denominator now, what number multiplied by itself is 64? It's 8. Boom, -1/8. So simplifying square roots. As it turns out, that you may end up with some kind of value to start out with. So what will happen is you're going to start out with some kind of square root. And of course, you'll have some kind of value in here. What we can do with that value is, instead of showing it as one number, we can show it as a product of its factors. So we're just going to be splitting these values up. And by the way, sometimes there's more than 2 factors that we can use in these square roots. But once they're split up into factors, we can actually split them up just like we did with the fractions. We can split these up as separate factors, but the square root of each. Okay. So again, right here we see that we're using 2 values. Sometimes we'll see 3 or 4. I mean, maybe up to 8 for a class like this. But the idea here is that we're going to be breaking up original values or a single value, I guess, into its factors. Okay. And again, if I haven't stressed this enough yet, I will again. Sometimes in mathematics, all we're going to do is we're going to take something and we're going to show it in a different way. That's what we're doing in this part of the lesson. We're going to take a value, instead of showing it as a value, we're going to show it as many values being multiplied. That's it. So while that may not make a lot of sense, it does give us some strategies for simplifying square roots. And one of the strategies will include, of course, memorization of those perfect squares. For now, of course, you have that printed in your notes, and so you can always refer back to that. So here's our 2 methods, and I guess I kind of bounce between these 2 methods, depending on which one is more convenient. But you can just find the greatest perfect square factor, okay, which means that you're breaking the value up, whatever the value they give us, into factor pairs, and you can look at all the factor pairs. You're just looking for the greatest perfect square factor, because again, you're going to be splitting that up, both factors, and then you're going to take the square root of both. It's just one of those is a perfect square, which means you'll have an individual value multiplied by some kind of non-perfect square root. Or you can just take the prime factorization. So prime factors, or prime numbers, I guess. Numbers such as 2, not 1, but 2, 3, 5, 7, 10, 11, 13. Let's see if I'm doing pretty good. 17, 19, and I guess list continues, but generally speaking, we don't see so much beyond 11, I guess. Okay, so all you're doing is looking for factors, these types of factors, for whatever value you start out with. Now you're going to break it up until you get all the prime factors, and generally speaking, that means that you're going to start with some kind of number, at least in the past is usually the way that they teach it, and then you're going to break it up into some kind of factor tree. If you find that one of the factors is a prime factor, then you'll circle it. If it's not, if you get another number here, then you break that up until you get some kind of prime factor, right? So circle the ones that are primes, and then that gives us a nice list to go off of prime factors. But again, it's that we're going to be rewriting that value as the result of its prime factors, okay? Now what we're going to be doing with prime factors is we're going to be looking for pairs of prime factors that match, because those give us perfect squares, okay? And when we do those, we're going to pull them out. We're going to take the square roots of those, and then we'll multiply all the values from the pairs and keep the non-pairs in the square root. Again, this probably doesn't make sense because we've never seen this process before, but I do hope it will make sense as we go through it. So these problems I'm going to do twice so that you can see both methods, and then you just choose which one you like the best. So square root of 72, again, we're going to do this twice, no problem. One's over here, one's over there. Okay, so let's start with this one. So this 72, I'll start with the first method, right? So I'm looking for the largest perfect square factor of 72, okay? So I know I could take 72 and divide it by 2. Well, that'd be 2 times 36. Okay, that's pretty nice. Well, I could also take 3 and multiply it by 24. I believe I can take, 4 and multiply it by 118. Not divisible by 5, but 6 works. 6 and 12. And 9 and 8. And that's all this is all of the factor pairs for 72. Now we're looking for the biggest perfect square. So let's identify our perfect squares here. I got 9, 4, and 36. Which of these is biggest? It's the 36. Which means that these other values down here, I don't need these ones, okay? Even though there are perfect square factors in there. I want the biggest one, which is 36. Okay, so square root of 72, right? I'm going to take the square root of 72, and I'm going to show it as the product of these two factors, 36 times 2. Okay, again, I did not change the value of 72. I just changed the way that it looks. And from this, give myself some space here. From this, I'm going to split it up, just like we saw 2 slides ago. So I'm going to take my two factors, 36 and 2. They're still multiplied, by the way, but I don't want the square root of them together. I want them the square rooted separately, all right? And again, that's okay to do that. But now I see that I got the square root of 36. That's a perfect square root, which is 6. And then we still got multiplied by the square root of 2, like this. All right, now on the assignment, they're going to have like a square root button they're going to push, and then you just type in a 2, push enter. Okay, so 6. You can push the multiply button, that shift 8 stuff, or if you wanted to, you could write it without, even on Canvas, okay? Because we hopefully remember that multiplication is the only operation that does not have to be shown. But these two are the same thing. Okay, either one will work. Okay, so there's our first method. Let's go to the other square root of 72 and use prime factorization. All right, prime factorization, I'm going to keep this square root of 72, and we're going to use a factor tree. Now, when I get to the end of this factor tree, when I finish off each branch, I'm going to show all of the prime factors multiplied together, taking the square root of each, looking for pairs. So 72, for me, I'd say probably 6 and 12. If I were to look at that, and maybe 9 and 8 would be better, but 6, neither of those two are prime, so 6, 3, and 2. You know what, I'll do 2 and 3, what the heck. And both of these are prime. Okay, well 12, that would split up with 6 and 2. 2 is prime. And then 6 splits up between 3 and 2, okay? And that finishes off each branch. So, square root of 72, I can write as a square root of all those prime factors. What do we got? 2 times, I'm going to rearrange this to make it more convenient. Hopefully that helps us to understand. I got 3 2s and 2 3s. So again, you can change the order from the commutative property. But now what I'm going to do is I'm going to take the square root of pairs, okay, and even the non-pair right there. So I'm talking about the 2 times 2, the 3 times 3, and then the square root of 2. These are all being multiplied right there. Okay, well, the square root of 2 times 2 is 2, and the square root of 3 times 3 is 3, and then we got the square root of 2, it's being multiplied, but that's not a perfect square because it doesn't have 2 times 2. Okay, so it's not even squared. This is 2 squared, this is 3 squared, and when we take the square root of a perfect square, we get these values. Finally, here I'd say 2 times 3 is 6, and again, we'll keep that square root of 2 right there. Well, that's the same answer we saw before, right? Let's just check to make sure. Boom, there it is. So you get the same answer either way. Now, is one method better than the other? Well, I don't know. You have to decide. When you get fairly good at this or get enough experience with it, you'll see that you don't really need to list all these factor pairs. And so for me, this method tends to be faster if we're dealing with small numbers. If I deal with big numbers, I tend to use this method. Square root of 120, nice. Let's do it. Let's do it twice because it's so fun. All right. So again, the first method I'll use here is I will take my 120 and I will look for factor pairs in 120. So I know it's divisible by 2. That'd be 2 and 60. And by the way, if you start with by dividing it by the lower numbers first and then move your way up, generally speaking, the first square root that you see is going to be the biggest one. Let's find out. Okay, generally speaking. So I know it's divisible by 3 as well. That'd be 3 and 40. Again, I'm not looking at any perfect squares yet. How about 4? That'd be 4 and 30. But I know 4 though. 4 is a perfect square, so I'll circle that. But I'll keep going. I know I can divide it by 5 as well. 5 and 24. Again, no perfect squares there. It's divisible by 6. 6 and 20. Not divisible by 7. It is divisible by 8 though. That'd be 8 and 1, 15. Okay, again, no perfect squares. Need more space because it has lots of square factors. It's not divisible. No, not divisible by 9. Oh, it is divisible by 10 though. 10 and 12. Oh, that's it. Okay. Well, there's only one perfect square factor in the set, and it comes from this one, right? So again, we're going to take the 30 and 4. I'll rearrange these so it looks prettier in the end. And we're taking the square root of that, right? Well, I'm going to take my 4 and my 30, and I'm just going to split them up into separate square roots. And I know that 4 is a perfect square for 2. 30, though, not a perfect square. So it has to stay separated. That's it. So there's our first method. Let's do the second method. All right. So 120. If I were to split this up, even in prime factorization, I'd probably say 10 and 12 and 10. And 12 we know 6 and 2. 2 is a prime factor. 6 is 3 and 2, both of which are prime factors. So we circle those. 10 is just 2 and 5. Okay, so 120, instead of showing it as 120, I'm going to take the square root of all of those prime factors, but I'm going to rearrange them into a way that is more desirable. 2 times 2, 3 2s, a 3, and a 5. Okay? Well, from this, do I have any pairs? Yes, I do. I have this pair of 2s, so I'm going to separate it. Okay, square root of 2 times 2. And then the other non-perfect squares will be separated as well. 2, 3, and 5. Okay? These are still being multiplied. But I know that 2 times 2 is a perfect square for 2. And then we can multiply that by the square root of 2 times 3 times 5, which should be 30. Well, did we see that before? Yes, we did. Let's go back. There it is. Same exact answer, 2 different methods. Let's address that. If let's say theoretically that these started with negatives in the front. Now, the nice thing if they're in the front is we can work those. If it's on the inside like we saw before, we say that it's just a not real solution for us. But if you have a negative in front like that, then all you're going to do is at the end, you make your answers negative. That's it. All right, so even on something like this, okay, so 7 times the square root of 12. Again, we'll do this twice because, you know, what's the fun in doing it once? All right, well, 12. Let's look, and again, for now, all I'm doing is ignoring the 7, okay? We'll get to that, even though I know it's being multiplied by the square root of 12. So I'll put the multiplication there, just so we don't forget. But 12, looking for perfect square factors of 12. That's, 2 and 6. Again, neither of those are perfect squares, but how about 4 and 3? Yeah, that's good. In fact, that's all the factors of 12 that we have anyways. Is there a perfect square factor? Yep, it's 4. So let's rewrite this. And again, for now, I'm going to ignore the 7. I'll bring it back here in a second, but let's focus on just the square root of 12, okay? So that'd be 4 times 3. Again, I'm going to split that up into the square root, separate square roots, 4 and 3. And yet, remember, these are still being multiplied, but square root of 4 is a perfect square for 2. Square root of 3, not a perfect square. So we'll just drop it. Okay, now I'll introduce the 7 back into the expression here. But we need to remember that it was always being multiplied by those square roots. So right here, it's being multiplied by the square root of 2. 7 times the square root of 2 is 14, and we need it to be fully simplified in order to give full credit. So it's 14 times the square root of 3. Boom. That's it. And again, just to address that question, if the 7 were negative out here, again, you can apply it throughout the expressions, but in the end, you would just make that 14 negative. That's it. So once again, I really am ignoring the 7, and that's okay because it doesn't mind. But 12, I can split up between, let's say 4 and 3, and then 4 splits up into 2 and 2. Now, I think if you guys get enough experience with this, you'd say, 4 is a perfect square. That's enough. All right, well, let's assume that you don't. So let's keep going here, okay? So 7 times the square root of 12. Again, I'm just looking for the square root of 12, which is 2 times 2 times 3. And again, do we have any matching factors there? Yeah, we do. With the 2 and 2, and then the 3 separated, right? So 2 times 2, and then 3. These are still being multiplied. That's a multiply. But square root of 2 times 2, that's a perfect square of 2, okay? So we see that really the setup ends up being the same. This one a little bit shorter process because it was a smaller number than 12. But yeah, again, this is where I would apply the 7s. Probably should have given myself more space there, but it's being multiplied by everything else. And we've seen that 7 times 2 is 14. 14 times the square root of 3, well, we've seen that already too. That's it. Now again, are you ever going to be required to use a specific method? You will not. So just choose one that works best for you. There is another method, by the way, but we can't go over it yet. We will later. In the meantime, here's our objective. 2 objectives. So hopefully we have the first 12 perfect squares memorized soon. And then we can simplify any radical. Really, when we talk about radicals, we're talking about square roots for now. There are other radicals. You got cube roots and fourth roots and fifth roots, but right now we don't care about those.